And I'm pretty sure it's more for you than for me. And during the break, one of you came to talk to me about, well, do you really need to know all of these things in order to do combustion research? The answer is always yes and no. It's yes and no because typically at your level, beyond the undergraduate level, when you go to graduate school and beyond, you always wanted to drive what you wish to know and how much you know by your research. In other words, how much you know is entirely driven by the problem you wish to solve. That's a transition. Early days, we take courses, we're giving exams. Those were just practice. Okay. Now it's the real game. The real game is you always gain your knowledge while you're trying to solve a problem. And a good scientist always know that for a problem you wish to solve, you're going to have to dig out what you need to know to solve it. And that knowledge goes into you. And you're going to keep it. So what I presented this during the last week was nothing more than those things, experiences that I had through years of research, that those things are helpful for me to do the research. Okay? You don't have to know everything. And you may have to know something more than we presented. And I'm pretty sure you know a whole lot more than we discussed here. Okay? Let your knowledge be driven by your research. Okay? And never feel bad you don't know you don't know something. That's good. Under that circumstance, either you don't know, but the knowledge exists in the literature, you just have to pick it up. And even more important is you don't know the answer or how to deal with certain problem, or you don't have the theory to do that, and nobody else have thought about it. And that's what I call methodology development. In science, and the combustion science in particular, methodology, in my mind, is still more important than the result itself. Okay? Spend a little bit of effort in developing methodology. Any day you find this thing has not been dealt, has not been looked at it before, and I'm going to have to find a new methodology to solve this problem, you ought to get very excited. Okay? Let's give you an example. The early generation of combustion scientists, there are many. I'll give you three names: Foreman Williams, Irving Glassman, and Heinz Wagner. Each of them, if you look at what they did in the long run, was about to develop methodology, about teaching us when you deal with a complicated, complex combustion problem, where do you start? Okay? So starting defining a problem in many ways is more important than closing the problem. Already. Among other things, yes, please.
Yeah, I just want to add a comment that I completely agree with you that research should be science should be research driven. Like I want to have an idea, I want to do methodology or a model, and then that should be the main drive for my research. I think currently it's more about the funding, like where the money is, and then go for that, and that's where my research is going. So, do you think like it's changing right now from Foreman William and these guys, and currently it's not the case to do that?
That's a good point. So let's stay on this issue. I know that during career panel discussion, this issue came up again and again. That's the founding. Scientists, but if you do not know, those 19th century scientists are mostly independent and rich. Lord Kelvin, he was a real lord. Okay? He didn't have anything else better to do, so he delved into science. So science in those days were done by very rich people. Okay? Today, as a scientist, you have to make a living. Indeed, you have to worry about the funding. But you have to think about one thing. Who came up with this idea? What area to be founded? You. Okay? At the end, it's you. Now, at the early stage of your career, you may not have that much influence in directing where the funding ought to go. Okay? But at the same time, you are contributing to the direction of the funding. And the trick that I figured it out, I gave you this example yesterday that I'm not joking. Indeed, the first year when I was a professor, I wrote 10 grants and I got 0. That was demoralizing. I thought I was no good. Okay? I went home and I said that I'm not going to write any proposal the second year. I'm just going to enjoy my work. I'll publish a couple of, hopefully, something will work out. And if it does, I'll publish them. Third year, I write proposal again. If I don't get any, I'll quit. Okay, and I meant it. So I really had the best time for my faculty career the second year. Didn't have to worry about the funding, just do the work that I really love to do. Guess what? That unfunded work had, by and large, defined the direction of my research in the next decade. Okay, I opened up something new, not drastically new, but new. And that got a funding agency interested. Eventually directed the funding in that direction. Okay, so the better way to deal with that is you do not catch funding. If you one day you become wherever you go. Okay, if you work for a company, you don't have as much freedom. If you work in academic world or in government labs, the best approach is fly under the radar the first and the second year. Do the stuff you love to do the most. Don't worry about the funding. Okay? Follow your dream. If you have anything new, anything, and it shows feasibility that can work, I can assure you funding will follow you. Okay? In that case, you're not working for funding. You are wanting the funding to work for you. Okay? Might be easily said than done. But that's the only way you don't become boggled down by funding. And I was fortunate enough that I really, after that second year, third year, I wrote 6 proposals and got all 6. It wasn't because the funding got better. It was because my idea got better. Okay? Then I will look back in the first year. Well, those 10 proposals I submitted were incremental science, they are crud. And I understood why I wasn't funded. All right. The other thing you probably have heard about it, the funding has a lot of politics. Yeah, everything has politics. But at the end of the day, you guess what? Those of us who've done enough of this, at the end of the day, my job, the most important thing of my job is to pick out a couple of bright mind. Go to funding agency, say, go fund him or her. You just don't know what good thing's going to come up. And I mean it. Okay. You have an idea, a good idea, that's a necessary condition for funding. Don't go the other way around. It doesn't help. All right. And never ever do where the money is, mold yourself into it. That life is no fun. Okay? Create your own game. And let funding to play your game, then you play the game of other people. All right. Do you want to talk more about this issue? Yeah, go ahead.
I have a question. When you said that yesterday, your suggestion about do what you love first, and before you have the funding, there's a certain limit to what you can do,
right.
And then if you're really interested in experimental science, that you might be fairly limited
right.
in that regard, or is there
right.
some other avenue that you can take that would allow you to do an experiment without
right.
funding?
What I said earlier, because early days I was a theoretician, I just do computation, I don't need that much money, and I can do everything myself. If you're an experimentalist, of course, it's harder. Okay. I don't know about the government labs, I don't know about industry, but in university, if you start your faculty career, you usually have a startup. Okay. If you have a startup, my suggestion earlier is don't go for fancy toys. Don't buy expensive laser. Start small. Start small because by the time you get a laser, you're already doing very quantitative problems. Your first problem ought to be a qualitative problem. Invent such a problem that if it interests you. And there are plenty of problems out there. Plenty of problems. Okay? Despite the fact we have this pioneer ahead of us, close their book, go for long walks, come up with 10 ideas, reject 9, and chase 1. Okay? Why? The beauty of science is that if you truly work on science, it doesn't have to work. It's all about what you learned in that process. Okay? And ideas morph in shape and form. And you can revise your idea in the process. Okay? If you can do that, then your first experiment may not be that expensive. All right. And the way how I started experiment, I was a theoretician. One day I got bored with modeling because towards the late 90s, I was doing a lot on suit models. We started to compare model against the model. We ran out of data. So I said, well, let me make myself useful. I'm going to do some experiment. And how did I do it? Well, it's because when I started my faculty career, I asked for $120,000 of a startup. I thought they're going to cut me by half. So as a computational person, $60,000, you buy 2 workstations, and that's how you're going to start. Little did I know, I asked for $120,000, they gave me $120,000. I bought my 2 workstations, I still have $60,000 left. Okay. And so I said, now what do I do? Well, you have to spend the money in 2 years. So you buy experiment stuff. What did I buy? Switch log, and with the help from my old friend, I got a flat flame burner in place, and I was learning how to do this stuff. And 5 years later, I have my first experimental paper published. It was very inexpensive. That experiment cost almost nothing. Okay. But that opened a new way how we measure soot in flames. Okay. So in the beginning, when you do experiment or do theory, for that matter, don't not do what have been done or other people are doing. Try something completely new. Completely new. Okay? And you will pick out something that works. All right, yeah, go ahead.
What are your views on applied research versus fundamental research?
Oh, that's not, early days I was a fundamentalist. That was because of one time I bumped into the chancellor of Berkeley, then Chancellor Tian. So he was a very charismatic person. So he said, oh, let me give you an advice. Politically, never be an extremist. When you come to science, be an extremist. Go for things big, small, the boundary, the edge. Okay? So, and do so as fundamental as possible. So I chased my dream of quantum mechanics. I thought really that's going to solve every problem. Okay. Later on, my mind started to change. Why? That has to do with the fact that once you write enough papers, the next one may come another one. And ideas don't always come every day. Not every paper I have drastically different new ideas. Okay. So you naturally have to wonder, well, what does this thing hold for? Okay. And what changed my mind was this. When I was a PhD student, I was doing this model, so-called Haka model of soot formation. We developed with Michael Frankler, and I thought this was a complete intellectual exercise. Who would ever put this stuff into an engine code? Yes, they did, and I did not know. So 2002, I was visiting Cummins, truck company, engine company. So they were very proud, and they told me that now they're developing the first cut design is based on a computational code. Okay. They do one experiment, then they tune the parameter, and they get the final design. The design cycle shortened from 9 months to 3 months. I don't know how much truth there is, but that's what the engineers told me. So one of the problems in diesel is soot production, and you have to be able to predict it. So my colleague, Fogel said, so what did you do with soot? The engineer said, oh, it's the Wang Franklin model. Okay. That moment changed my life. Suddenly I realized that when I drive on the street, I saw a big car driving by, truck driving by. I said, I may have something to do with that. So in addition to the paper you publish, of course you're proud of your intellectual output. You also are making a difference, big or small. So since then, I do not distinguish fundamental and applied research in my mind. As long as it's a challenging problem, I'm more driven by the problem I have to solve rather than prettiness of the science I do. Okay? My view is, applied or not, if you do it well, it will turn itself into fundamental problems. Because the natural inquisition of mind forces us to take a very complicated problem, decouple it, and asking a question one by one. And that's a fundamental approach. There is no fundamental difference in my mind between applied and a fundamental work. Okay? It is all driven by the problem you wish to solve. The other thing that not many people hold this view. As fundamental as I do in my research, I believe at the end, whatever I do ought to have an application. And I maintain that if you look at that era, 19th century science development, for every Boltzmann, there are another 100. You don't hear them anymore. Go to open up Physical Review, the journal, published in the late 1900s and early 20th century. What you will find is many names, beautiful science, beautiful, but you don't hear them in textbook anymore. Why? Because it wasn't useful. Okay? We still study thermodynamics is because it's useful. It guides us. It guides us to understand certain things. All right. So those are more or less my point of view. Other things. Am I done with the closing argument? All right. So if I don't have a chance to say that, this has been a great week. I'll continue this discussion here, but this has been a great week, and I learned a lot from you. If I were to close anything, I just want to say that your job, if you stay in the combustion field, is to prove what I presented this whole week irrelevant in about 20 years. Okay? You're going to have to find a different way to deal with this problem. And I don't want it to go in there too much because it may not do anything good. The way how we approach combustion problem, at the end turbulent combustion, I'm not sure we're taking the right approach. Okay? And you're going to perhaps think about what I say and come up with a different way of dealing with the complexity of the problem. All right? So I'll continue on this topic. So, so the way we handled this is this. We have the response surface we already talked about, first order sensitivity coefficient, second order. Now, you're going to have to deal with a spectral representation of uncertainty in the rate parameter or other model parameters. Okay? And based on, depending on the distribution you choose, the representation can be somewhat different. Okay? And this is essentially Gaussian distribution is inherently defined as such. You then combine those equations together, then what you find is a prediction for example, a flame speed as a function of model parameters and their uncertainty. Okay? So it's all polynomial representation of this problem. Then the remaining issue is about how accurate the second order polynomial has to be. It is. And if it's not enough, always expand to higher order. It's just computational cost. Okay. For now, in fact, even first order is good enough. So how do you develop a response surface? Suppose I have 3 rate parameters, okay, you're interested in. K1, K2, K3. All right. There's a composite factorial design with a statistical method. Long story short, if you have 3 parameters, you do calculation, for example, flame speed or ignition delay, at the corner of this uncertainty box. Okay? And this box represents the combined uncertainty of the 3 rate parameters. You do it at the center, the 8 corners, and what I call the star points extending the axis out, creating a pseudo-spherical effect. And once you have this calculation, you just fit it into a polynomial. Okay? That's the most rudimentary way of doing it. Now, if you have 20 parameters, you run into a problem with this method, because you have to do 2 to the power of 20 calculations. All right. Now, if you go to this book by Box, 1978, he has ways to get around with this problem. It's called fractional factorial design. It allows you to cut corners. It allows you to miss some corners. Okay. So if you have a 20 variable, most likely you only need to do 2 to the power 8 calculations. That's still allowed. And the other way we're going to do that is simply by doing sensitivity analysis, first and second order. Okay? And through that, you can construct this surface simply based on Taylor expansion of what you wish to predict with respect to the model parameter you are interested in seeing its impact on the prediction. I presented this part earlier, and this is what I said is a statistical sample of the uncertainty in our kinetic knowledge for hydrogen oxidation. Okay? To prove I'm right, David Shin used this uncertainty method and predicted a band that's bracketed by this dashed line. This is how I throw all of the uncertainty of the rate parameter into the pot and do the calculation. And this is the 2 standard deviation. This is the nominal prediction. This is the 2 standard deviation of the model. This dot dashed line represents this curve. Okay? Clearly, all of the model lie within the uncertainty of individual rate parameter. Therefore, it is consistent that we view this is essentially statistical error or uncertainty we're dealing with. Okay. Now, given this picture, I presented this quite many times in combustion community, and by and large, this idea has been totally ignored. Nobody pay attention to me. Keep saying you guys are doing statistical sampling, and you're providing 1 point. And I thought that was an insult. Everybody just smiled at me and said, "Get lost." But this is when I'm getting somewhat frustrated, that unless you disagree with me, then you must consider this uncertainty in your model development. Or else, forever, you're going to do a random point within the knowledge that you know. Okay? But now, once you have this band, you can ask several questions. If you give this to an engineer to use, or rather engineer is using this model, is this model give me accurate enough knowledge that I can rely this on to develop my engine? Obviously, for hydrogen mass burning rate, you see at 25 atmosphere, my variation is a factor of 4. Meaning, taking a simple example, the flame length versus combustor size, you're uncertain by factor 4. I don't think you can justify to your manager to design an engine based on this accuracy. Okay? So the remaining question becomes, with the knowledge I have, that's the experimental data. How do I use the experimental uncertainty to constrain the model uncertainty? And then when you do, and after you do, you ask the question, is that enough? Okay. The other aspect of this argument is now you know how accurate an experiment you need to do to provide modelers with useful knowledge. Obviously, if this measurement has uncertainty that extends the whole chart, it provides no information. Okay? If this uncertainty lies inside of the model uncertainty, then you offer quantitative information. All right? So how do you do the next part? Next part is constraining the uncertainty. So we started with a large parameter uncertainty. Now you have a smaller data uncertainty, and you have a prediction that's over here. Over the time, what you hope to do is to take this data uncertainty projected back to the model, getting a smaller region of parameter space in which you're going to be able to predict all of the data that you consider. Okay. So this is a backward projection of experimental data onto your model space. Yeah.
But this is done only for one kind of experiment.
We usually consider a large range of experiment. You don't have to, I just use laminar flame speed as an example, but we'll follow this up by considering hydrogen combustion. We actually used 60 sets of data, including flame speed, ignition delay, detailed species profile, flow reactor, and so on. All the good data that we can find. Okay? Let's skip this. So at the end, what did I do is quite simple. I go backwards. Now, this idea can be represented in a two-dimensional space. You have two rate constants, K1, K2. Assuming that I don't know much about a K1 and a K2, I shall assign an uncertainty bound. This upper uncertainty bound might even be the collision limit. Okay? The lower uncertainty bound can be chosen based on experimental uncertainty, the scatter, or a physical knowledge for the reaction rate. And this typically, in our case, this uncertainty spans, in good cases, like H plus O2 chain branching, 25% up, 25% down. But in most cases, this uncertainty spans factor of 3 up, factor 3 down. So you're covering one order of magnitude of uncertainty. In some other cases, for those rates that have never been measured, you're going to have to assume a factor of 5 up, a factor of 5 down. So the assignment of uncertainty isn't ordered itself, and that will require some theoretical development. But for now, since I have experiments downstream, I'm not so concerned about this, especially when I have many. So what you are trying to do is, given this initial uncertainty, you want to find a combination of K1 and a K2 that will predict the data you consider, the full set of the data you consider, all within their respective uncertainty. Okay? Obviously, the precise knowledge occurs if and when you can shrink this red band, the feasible space, down to a single point. And you will never be able to. But from an engineering standpoint, you need not to shrink this down to a single point. You just need to shrink this feasible kinetic space that can reproduce all of your data to the point that when you design a combustor, you say, well, I can be able to design a combustor with 90% certainty. I just need to take this combustor 50 centimeter plus minus 1 or 2 centimeter. It's a fully constrained problem as far as engineering is concerned. Okay? But then this also becomes a streamlined, better organized work, because as far as the physics is concerned, the reaction mechanism of hydrogen oxidation is solved. That problem is solved. To the point, I don't believe we should publish more papers anymore. You publish paper because you want to solve a physical problem. Okay? The remaining quantitative problem, how accurate it needs to be, that answer comes from engineers using your model. Okay? You're only going to see pathway changes. And all the rates are accurate to within factor of 2 for hydrogen. That's good enough. Okay? Then if engineer use it and they say, look, it'll cost me $1 billion to build a prototype. But I have this model 3 times more accurate. then I can avoid building this prototype, spend that 1 billion. You ask a question, how much does it cost? Maybe 1 million. One of you have to do a critical experiment or set of critical experiments. Then it becomes a constrained problem. A constrained problem that is not like what we often do, making what I call random measurements. Okay. You understand my argument, right? Okay. So I believe in the long run, you're going to have to approach combustion science quantitatively that way. That doesn't matter how you're going to solve this problem. If you're going to solve this problem through a model, model will have uncertainty. Uncertainty have to be addressed. Well, your job in science is about making sure the physics is there. The uncertainty in the parameter is an engineering problem, but that's problem dependent. If you design a combustor, you can allow reaction to reach equilibrium. All this problem disappears, right? Because after all, thermochemistry is much better known than rate parameters. Okay? So the accuracy model is problem dependent. And more specifically, it's engineering problem dependent. And let industry to define what accuracy you need. Propagate this information back to the academic world. And for those of you who play with lasers, you're going to think, how do I measure OH now to within accuracy of 10%? Because if I can do that, I'm going to be able to constrain the model uncertainty to what GM or Ford or Volkswagen needs to have. Okay? So science, engineering now, essentially, in my view, becomes one single, same problem. So the backward projection of uncertainty, the goal is that you take this representation of what you wish to predict and the impact of uncertainty from rate parameters or other parameters into a prediction for the fuzziness of what you wish to predict. Then you essentially do least square minimization. It's not fancy. You take the response surface, that's this thing coming over here, plug it in. You have some observation. You weigh the observation or minimization by the uncertainty of the observation. Okay? Then you also consider the experimental uncertainty of the measurement and also weight over model. Oh, sorry. This is your rate parameter itself weighted by its uncertainty. Okay. Through this minimization, what the goal is to minimize this function with respect to a new set of parameters so that you can ensure the model prediction is the best, gives you the best fit through all the data you wish to have. That's not ad hoc tuning. That's inverse problem. Okay. And then you can also do the same operation on the uncertainty of the experiment. Okay. Through that, you can also develop, this is basically the covariance matrix. You're going to ask the question, how the impact of what is the coupling of two rate parameters. I'll explain this a little later. Don't worry about the math here. Okay. But this is the basic idea. So to answer your question, we actually consider a large range of experimental data for, in this test case, for hydrogen CO combustion. 12 laminar flame speed, 30 ignition delay, 9 flow reactor, 2 laminar flame profile. And the second set of data is from Princeton. That's 18 data points used in the constraining process. So the question I'm asking here first is that what is the impact of that new set of the data in our quantitative knowledge of hydrogen combustion? So this is the mass bending rate as a function of pressure. This band represents initial uncertainty of the model. So if I consider the first set of data, what I call experimental knowledge prior to the Princeton high pressure flame speed data, I have this band. Okay, I have this band. That's my remaining uncertainty in model prediction. But then if I add the Princeton data set, my uncertainty band becomes even narrower. In that form and shape, the knowledge of kinetics at least this progress of it can be measured. And you want to do that, yeah.
I just want to make a point here. I feel that with data set 1, you had certain level of accuracy, some uncertainty.
Yeah.
It is very likely that with data set 1 plus 2, the uncertainty grows. So it's not necessary that the uncertainty would go down.
Ah. When you combine both sets, and if you realize when you combine two data sets, your prediction uncertainty widens. That happens. There's a physical reason for that. Number one, there are two physical reasons for that. When that happens, it's indicative that if the data are accurate, then the model is incomplete. Mathematically, if model is complete and data are accurate, this should never happen. It's because this experiment pulling you this way, that experiment pulling you that way. You end up with bifurcation of a two-ray parameter space. That's impossible mathematically. Now, that physically is impossible. So either you're missing physics. A lot of time when we do this exercise, we find that if I include a new set of data, the uncertainty actually expand. Okay? And through that, we actually often find missing pathways. It makes you think what's missing. The second possibility is data, one or more sets of data are inaccurate. That happens too. In this case, I know the physics is complete. So when that happens, it must be data inaccuracy. So we have a ways, David have developed a method to determine which set of data is the greatest suspect. When that happens, I typically send an email to the PI of the author, principal author of the paper, say, look, could you look into this? Because this is what I'm going to say if I'm going to write a paper about this topic. Could you be off by this factor? Okay, yeah.
Another point here, I think more than the model being incomplete, I think the more common problem is that the model is usually redundant. So there are a lot of reactions that we actually don't need to have there, and that are part of the model. Mm-hmm. And that's one of the reasons why you see that for different data sets, different models fit very well. So what is happening over there, I guess, is that the model is overfitting. It's fitting very well to a particular data because it has a lot of redundancies.
Yeah. So one of the things that if you, following what you just said, I agree with you, and my suggestion is this. I've seen this very often. You develop a reaction model, you verify this against one single set of data, not single data point, but single set of data. Maybe a flow reactor, maybe a stir reactor, maybe a laminar premix the flame, maybe in shock tube. And that is a very dangerous way to publish a mechanism because your mechanism model is going to be picked up by someone else, and it shows it doesn't predict the flame speed altogether. Okay. Now, for me, I'm very thin-skinned. When that happens to me, I'm getting very uncomfortable. All right. So over the years, one of the things that I try to do is whenever I deal with a reaction model, I always make sure that I will cover as wide range of experiment data as possible. So for example, if you, now this is, we're moving all in that direction, the field today. I always advise you, if you develop a reaction model for a particular set of experiment, always at least run the flame speed in addition to the experiment you wish to compare your model to. Why? When you verify your prediction against the flame speed, with data, without data, if you know the adiabatic flame temperature is around 2,200 Kelvin, you can guess the flame speed is around 38 centimeters per second for stoichiometric mixture. You're never going to be around that much. Okay? Laminar flame speed don't necessarily tell you that your model is correct, but it's very good at telling you when the model are wrong. The argument is if you cannot reproduce laminar flame speed, something really, really bad is in your model. So that is an easy way to check to make sure you don't goof too much. If you get a laminar flame speed right, you will get a global heat release rate right. Then you deal with the detailed stuff. Those are the species profiles. I made that mistake, and I'll admit it to you. My most cited paper, this pH paper, I did not do that. I regret till today, because that was the pH formation mechanism for ethylene and acetylene. 10 centimeters per second too high for the laminar flame speed of ethylene in that paper. It haunted me till today. All right, always do a laminar flame speed calculation. You learn a lot when they disagree. Okay. But if you want to push more, it never hurt grabbing all the data from the literature for a particular field with the mechanism you wish to develop and do the validation on it. Okay, single set of experimental validation is often dangerous. All right. So then, if you look at other curves, other conditions, sorry, you can't see it very well. These are for other mixtures at a different equivalence ratio, again as a function of pressure. The model after constraining do very well against a large range of data. Simple experimental data, the solid line is after constraining, the dashed line is before. Then what did I do? In that constraining process, constraining the uncertainty, what did I actually do? And second question, what did this set of new Princeton data offer us in knowledge? So if I use data set 1 only, what I found is the data are providing constraining, the shaded area represents essentially impact, okay, on the rate parameter. When you have a darker square, it means the experiments are constraining that particular rate constant. And if you go diagonal, this is the variance on the rate parameter itself. If you go off diagonal, that's the coupling. Yeah, go ahead.
What is the x-axis in this?
I'm sorry?
What is the x-axis in this?
What is the x-axis? Oh, okay, sorry. Let me explain. This is a 45. This is essentially, we are looking at a list of reactions. Okay. So on the top, I have H plus O2. That's the first reaction, the second reaction, the third reaction. So I'm plotting the variance, sigma ij, I being reaction 1, j being reaction 2, and so on. Okay. What this chart tells us is the variance. The variance, what is that? Physically, what this means is that the data I considered impact A, the rate value themselves, but also it impacts the coupling of the rate. Okay? Initially, my rate constant occupied this space. When I considered all of this experiment, I cut out half of this space. I said, well, over here, I just cannot reconcile all the prediction. I'm here. Then you also have diagonal. That is a coupling of two rate parameters. Because of the coupling, you chop this space further. Okay. So, in other words, the more useful the experimental data set you consider, the darker this matrix has to be, the more information to provide. So those are basically, the other way to interpret this is information matrix. Okay. If it's all white, your experiment provides no information. All right. So between here and there, as you can see, what that impact of the Princeton data did is from here to there, you see a significant narrowing of the uncertainty. It's because it had an impact on constraining of more coupling of the rate parameters. Okay. So the other way to look at this problem is this. If I plot the H plus O2 chain branching versus H plus HO2 producing two OHs, those are high pressure flames, so HO2 chemistry is critical. All right. The circle represents the contour of the probability density function of uncertainty. So if I have another axis that can stick out from the surface, then this is just a symmetric Gaussian function. Okay. So when you throw all of this data onto it, then I find an elliptical space in this 2 rate parameter space. I say every point inside can reproduce my experiment. In other words, every point inside will give me prediction within this band. Okay. So the powerfulness of this method is, as you can see, if you wanted to use a reaction mechanism to predict something, and predict something accurately, you need not to come to a point in the space. In fact, from the circle to the oval, the space volume has been shrunk by a factor of 10. But you actually need not to have every rate constant to be accurate to within 5% in order for you to make reasonably good prediction. You see my point? Okay. This result also tells us direction for the next experiment. The next experiment is in this direction. We've already had enough data, giving me enough constraint. In this direction, I actually don't have good enough data. So now the problem becomes, how do we go backwards and design an experiment so that I can cut across this oval and get a smaller space? All right? Experiment will become small experiment. All right? And that's indeed what we are developing as a part of this EFRC strategy. So next time, what we hope is that by end of this EFRC effort, with this type of analysis, we will be able to crank the computer code. The code will spit out a set of conditions, for example, an extractive condition. Then we'll be able to go to Stanford and say, well, do this experiment at this temperature, at this pressure range, for this range of a field stoichiometry. Moreover, I need you to do this experiment with 10% uncertainty in both the time scale and in the vertical mole fraction scale. Because once you do that, I will be able to cut across this oval, get a substantially smaller space. So that's a methodology development. In the long run, if the methodology is developed, to me, half of the combustion chemistry problem is solved because we will let industry to tell us, is this good enough for you? And they will run those codes and come back with specific questions. They will come to Princeton, say, Professor G, I need you to do a measurement of flame speed. At that pressure, that unbounded gas temperature, that equivalence ratio, I need uncertainty plus minus 1 centimeter per second. If you can do that, then my engine design will be constrained to the level I don't have to spend that 1 billion. For that, I'm happy to give you 5 million. Okay? So this, as I see, at the end, science founding, those are problems you create in order to solve a problem. We go back to you asking applied fundamental. To me, this whole thing is the same thing. At the end of the day, our goal is to solve a practical problem. Practical problem leads to scientific development. Now, then from the standpoint of people who do measurement, at Stanford, say, I can only do 20% uncertainty. How do I get to 10% uncertainty? I need a better laser. I need a better optics. I need to play with optics, diagnose this better. Those are science. Okay? Like measuring the Hubble constant. Because what you seek to find is the universe will continue to expand, or it will shrink. That's a big question, right? But it requires you to measure the second decimal place of the Hubble constant in order to make that prediction. Oh, then you have to develop all kinds of methods. That's science. All right, so it's problem-driven, except for here, there. In the physics problem, we're dealing with our fate, our universe. Here, we're dealing with how good an engine you design. So the same problem. All right. So,
May I ask
yes, sure.
This might be a stupid question. I'm of Denso Corporation from industry, and from engineering point of view, sometimes what is important is not only the flame speed itself, but also the uncertainty of the sensitivity of pressure or temperature to the flame speed. So, what we are talking about uncertainty of the flame speed, does it mean that the true values should be plotted randomly on the uncertainty band, or there should be some tendency to the pressure or temperature is guaranteed?
Okay.
That is monotonic increase for the pressure or monotonic increase to the temperature.
Okay, let me understand this. You are worrying about uncertainty of the flame speed with respect to the uncertainty in your boundary condition, that's the temperature and pressure of the flame. You are worried about uncertainty in the laminar flame speed from the temperature, unburned gas temperature, and flame pressure.
Yes.
Okay, so what causes the uncertainty in the temperature and the pressure? You mean the measurement uncertainty? Or this is inside of the engine, you are uncertain in temperature and pressure prediction?
Yes, that means in industrial design, when we design some industrial products,
Yeah.
we change many parameters. And what is important for us is the sensitivity of each parameter
Right.
to the final value.
Correct, yeah.
So at that time, for example, the flame speed itself is not necessarily important.
Okay.
So
But temperature and pressure, yes, local.
yes.
Okay. In principle, what this method can do is, as long as you have a model, you can apply this method. Because the flame speed is just one example I use to illustrate the idea. We can do this for ignition. We can do this for temperature as a part of a solution to the energy equation we solve. We can solve for pressure because that's part of the governing equation through the equation of the state or whatnot. We can do all of those in principle. Okay. As long as you have a model, you have the uncertainty, you can predict all those things. Numerically, it may not be easy for a time-evolving problem. And that's the second thing we're working on. How do you, flame speed is an eigenvalue problem, it's a steady state. You have rate parameter uncertainty, you get a steady state prediction, and you get uncertainty. How do you deal with time-evolving events? Okay. What you wanted to calculate is the nominal value. With this uncertainty, you want to follow this uncertainty over time. But now you have uncertainty will lead to coupling of uncertainty, and they shall expand over time. Okay, sometimes uncertainty kills each other at the end. If your goal is predict equilibrium, the uncertainty initially will expand and eventually shrink into a single line. If your thermochemistry is known, so it depends on the question you have. But that's the second question we've been dealing with: time evolution of uncertainty. That problem mathematically has not been. Mathematically, it's not too difficult, but computationally, it's demanding. Okay, but it's possible to do it.
I have a question.
Yeah, sure.
So, apart from the measurement of uncertainty in the y-axis, which is the measured parameter, there can also be an uncertainty in the parameter which you measure as a function of. For example, there is always an uncertainty in the temperature or the pressure you measure
Sure.
it against. So,
Yeah.
how much do these models account for such
Right.
independent parameters uncertainty?
Mm. So I appreciate your question. My assumption is the following. Not always right. A good experimentalist knows how to assess his or her uncertainty, considering every parameter on the one hand. On the other hand, in combustion literature, only the last 10 years we've seen uncertainty bars expressed more often. Okay? That was after some of us pushed and pushed and pushed to the point that we had to threaten often that if you don't give me uncertainty, I won't want to agree to let your paper to be published. Uncertainty in experimental measurement is critical, and the same argument can be made. The modeling is all about uncertainty at the end to me. Experiment is also about uncertainty. Okay? It is uncertainty, and that's another thing, that those of us who work in physical science often see uncertainty as a dirty word. I use the word uncertainty. The other way to say this is error. When you talk about error, what do you mean? My burner has errors? Okay. So we usually don't like to deal with uncertainty. Uncertainty is annoying. You always like to have uncertainties in life, right? You want to go to a party, you want to get there at 7 o'clock. You say, what time do I have to go? You worry about traffic. What are you doing? You're worrying about uncertainty. Life isn't always about uncertainty when you try to do something right. Okay. So in my view, there's nothing shame of telling people that how imprecise your knowledge is. And if it is, you really, really know everything, then you're probably not working on anything important. If you go prove Newton's law is correct, second law, F equal to ma, sure, you can measure gravitational constant to 4th decimal place, no problem. Right? But that's not an important problem because it's solved already. Anyhow, going back to this plot. So when Professor Wang at Stanford sent me this plot, I was mighty proud. Okay? After all, we had a model first, then he had an experiment. So, well, I'm doing something right. David said, well, don't get too excited. An apparent agreement does not mean you're precise. Now, I'm sorry that you can't really see it clearly. You see these little dots? Okay. This is the same plot that I showed you earlier, except for now I expanded this into separate plots: ethylene, OH, water, carbon dioxide. The solid line are experimental measurement. The dotted lines are model prediction. This is otherwise you would run the chemical code, integrate the species concentration, you get a line. You put onto experiment, you said this is a good prediction. We said, wait a second. While the model is accurate, nominal prediction is accurate, how certain is this? And what is its precision? Precision is measured by uncertainty in array constant. So those dots are Monte Carlo simulation results, considering all rate parameter uncertainties. And this is not a pretty picture. You see, for example, CO2 over here, we're dealing with an order of magnitude up and down in the prediction. Okay? So the next question we ask is, well, since the experimental uncertainty in this curve is 10% up, 10% down, and if you consider the time scale, the temperature uncertainty, you add another 10% as a 20% up, 20% down. That's much better than an order of magnitude. So experiment gave us some information about what we can do. We took jet surf. Again, not only we took this set of Stanford data, we also took laminar flame speed and ignition delay measurement from the past. We also took some species profile from various sources and do the reverse constraining. So this is unconstrained. This is constrained. So that shows the utility of this set of experiment. When you get uncertainty very well good, then you can constrain the precision of the model down to about less than factor of 2. Okay? If you can't see it, there are many dots here. These dots, the spread of the dots is substantially narrower than original. And that's how we can approach from a fuzziness in knowledge to a more precise knowledge. The other thing I thought was fun to look at it is we do shock tube measurements, we do flow reactor, we do laminar flame speed. Are they related to each other? If I do a good shock tube measurement, how does that impact my accuracy for prediction for laminar flame speed? Is the question we're asking. So in that way, you can measure the value of your experiment. Okay. So if I consider no experiment, this is for heptene combustion. Laminar flame speed as function of Queen's ratio. This is band representing my initial model uncertainty. When I consider the Stanford shock tube data, I get an uncertainty band width down by about a factor of 2. Okay? Now, this gets people who do laminar flame speed measurement a little nervous. Oh, do you still need us? Founding, remember? You're taking our job away. If I have a shock tube, I can get uncertainty down to the level that you need. Then you're out of your job, right? Well, it turns out this test shows no, you still need people measure laminar flame speed, because even though I can use one set of shock tube data, just one set, fire up your laser, get a species profile, I can get uncertainty in the flame speed prediction down by a factor of 2. To go, if you want to do better, you still need the laminar flame speed data to constrain it between here and there. All right. In this way, you can start to ask a very quantitative question for various experiments we typically do. Okay. A, what's the utility of those experiments? How accurate this experiment needs to be? That gives the justification for founding, you see. So after saw this, Professor Wang Hansen get very excited and competitive. After all, this is the first time somebody showed the relationship of his measurement to properties that he doesn't measure. Okay? He said, can I get a measurement? What accuracy do you need so that I get to here straight? Taking away all the flame speed measurement. I told him 1%. He get excited again. Sure. Let me get some really better laser and I fiddle with the diagnostics to get even, try to get to 1%. That's founding. Okay? When you constrain the problem in a way that is logically sound, it's just a process how you're going to get there. How can a founding agency say no? Of course, you have to go talk to the industry people, say, well, is this something you would consider? Okay. Maybe I won't be able to give you an answer this year, but I may be able to give you an answer next year. When you have impact, when you have a logical development that makes sense, when you have potential for a capability to do this measurement, that's founding. All right. Anyhow, yeah, go ahead.
I think there's one more thing here.
Yeah.
When you are doing flame speed measurements, and if it's fitting fine, it's okay. But say your deviation becomes larger, it doesn't really mean anything because it might be because when you're predicting it, you might be using wrong transport coefficients.
Mm-hmm.
So are you considering adding those uncertainties?
Yeah, well, what I'm doing here is methodology, remember? Since the rate parameter is the most difficult thing to consider, I'm going to do rate parameter first. From outline, you can consider the boundary condition of the measurement. You can consider transport coefficients, and you can consider thermochemical data. In the long run, if this sort of things goes to turbulence code, you can even consider your turbulence parameters in them. Mathematically, they're not different. It's just a parameter. Beyond that, it's all about the fitting, getting a response surface to save you computational time. Okay, so you're absolutely right. And the other thing you have not asked me is that so far I've assigned uncertainty temperature independent. I just yanking a factor to the rate constant. Can you do this on activation energy? Can you do this separate on A factor? Okay, and those problems becomes problem dependent. It depends on what you wish to learn. Next issue is transport. We won't have time to talk about the transport. Indeed, there's a lot of uncertainty on transport. Okay, and I will hope to spend 5 minutes just pose some questions, and perhaps you guys could look into it. All right. Fundamentally, I can deal with all this problem. Okay. For laminar flame speed, usually, other than the hydrogen flame, you don't get much sensitivity from transport. Only for hydrogen flame you do.
Well, but say
think of multi-species diffusion, right?
Yeah.
You can't really do it. It's so many, right? If you think of it, so many species, each species dealing with each other.
Yeah, well, if you go to large hydrocarbon, of course, right now, if you do thermal diffusion plus a multi-component transport formula, you get stuck. So those are, you know, realistic problems that you have to deal with. And in the long run, I would say that for fluid speed calculation, one of the things you should avoid doing is always using detailed model. What you wanted to do is get one convergent solution and simplify the model down to something of 50 species. Okay. There isn't a single hydrocarbon fuel molecule that requires more than 50 species to predict the fluid speed. But watch out, there are times that you're chopping out the parts mechanism that may matter for prediction. Other questions? All right, so let me just, so this is what this is our detail. I don't want to go into too much beyond that. This is Bing stuff. So I use the word our approach. I actually don't know who our is. So far, it's just me. Okay? So far, just me. So the way how I dealt with this problem with reaction model development in the past is that I'm taking an inward loop. Inward loop, that means you have to chop out publication as the component. I talked about why I don't publish earlier, which, by the way, I said earlier this week that I don't review reaction mechanism papers anymore. I systematically turn them down because I just don't know how to review them. Okay, you have a 3,000 reaction mechanism. In the older days when I do mechanism paper review, I literally look at each and every rate parameter. I sometimes pick out rate parameter that is wrong. Okay? And other people review my paper have done the same. So I don't agree with your K5 because I did this measurement, you're off by factor 5. We go back and forth arguing about it through review rebuttal. At the end, either we both lose or one of us lose. But in the process, either the reviewer or I always learn something. And that's the correct, really the right way of doing the review process is really full. Now I don't review paper because what? You want to expect me to look into 3,000 rate parameters? And if I don't, I haven't done my reviewer's job. All you want me to look at is do lines go through the data? If it goes through the data, I don't know if your model is good. If it doesn't go through your data, I get excited, I look at your sensitivity analysis, sensitivity spectrum, then I get stuck from that point. I have all these ideas, sometimes write 3, 4, 5 pages, come back with, typically the author say, oh, that's for next paper. Okay. And I'm sympathetic to the author. Indeed, what do you want him or her to do? Redo the whole thing, the student must write a thesis and graduate. Okay, and I don't want to give students a hard time. Those are problems I don't have answers. So I decided not to review them. However, one day, if any of you use this uncertainty method, then I'll review it because I have my scientific justification. Now, again, okay, I need not to look at it into every rate parameter, but at least I know how certain it is the knowledge, and I can ask questions from that standpoint. It's not a strong argument, it's a weak argument, but that's my necessary condition to be a reviewer. It doesn't concern you because it doesn't impact you at all. It just gets editors very annoyed. Okay? You get the papers from my colleague, Factorial, keeping decline. When I said, just don't send me those papers anymore, I won't review it. I told the same thing to Philip de Gaulle. Don't send me those stuff. Anyhow, so the approach that I like to take is an inward approach. That you can get reaction mechanism published on the web. People download it. You don't need not to publish it. If it's good enough, it saves you all of the time collecting reference and so on. You do get a big hit on your impact factor. You know, You apply for jobs today, you're going to have to worry about number of paper you publish. Moreover, they have to look into your H factor and so on and so forth. Now, if I publish every reaction mechanism that I worked on, my impact factor would have been increased by a factor of 2. Okay, it does impact you, your career. But there are times you have to stick to a principle, say, well, okay, that's the right way to do it, and I'm not going to do this for my own good. I do this for the community, and I really believe that. So the inward approach is that you have the inner loop to make sure you have all the physics. You have accounted for all the pathways, okay? And that's a inner loop. Outer loop is you develop a response surface, you analyze the uncertainty, you come back to the validation. And when it happens, typically you have a couple of unsolved problems. You go back to various labs in the world and say, well, can you do this measurement? And that works out for me, and it worked out for me very well. And that's how developer now, speaking about the founding, if you're able to do that, that gets everybody excited. You're all working on a common goal. It's difficult for one person to knock on founding agency's door and say, I want to do that. It's next thing you have 5, 6 different people all in your committee and say, we all want to do that. Okay? When we all want to do that, founding becomes easy. All right. So for that reason, I do mean that you have a substantial influence. If you have a good idea, you want to solve a problem, founding is always going to be there. And instead, my student Xiaoqing, you sit there and she is not complaining. Okay? Instead, where do the paper, student, you want to graduate and you have to write papers, you have to write thesis. Where do this paper come from? Well, there are fundamental questions and problems came out from this exercise. One example, CO plus HO2, rate constant. That's one of the major chapters of Xiaoqing's thesis. Came out with experimental data is substantially higher than what do you need to reproduce RCM data. That becomes a science question. And then you do a very nice rate constant reaction rate theory paper and you publish it. Okay. So that's my approach. So those are the people I've been working with on this project, and I want to acknowledge them, so we're not done yet. You're talking about, let me close this now. I didn't prepare anything. I actually have something that, but I just don't want to find it on my computer. So let's talk about transport problem. Okay. Let me identify. Yeah, go ahead.
Just something quick at the end. So is there a reason why you picked second order as far as like looking at the reaction sensitivity to 2 reactions together versus 3 or 4 or 5 or 10?
Yeah. The third order effect, we tested it. The impact is very small. I still want to explain the mathematics. For a chain reaction mechanism, you would expect much higher order interaction. For example, if I push the chain chain branching rate up, chain termination rate down, you will see that the reactivity must increase, right? That's understood simultaneously. But at the same time, if I yank in a heat release reaction, H2 plus OH producing water, I should see even third order coupling. I don't see that many. So that problem mathematically I still don't understand and needs to be explained. Okay. A part of the problem, of course, you do any expansion type of problem, you're always going to wander somehow down to the end. Okay. What are you missing? What are the high order terms you truncate? So far, we tested the high order term, not much. So, and on the other hand, in the long run, it would be fun to design an experiment to give you as high order coupling as possible, because this experiment is going to be very efficient in narrowed joint uncertainty space. Okay, so we are working on this type of problem mathematically, basically designing the most intelligent experiment. Okay, a couple of critical experiments get to what do you want to know. Yeah.
And the second one is, so we, in our group, we're basically purely experimental. So we look at simulations a lot, and what I'm wondering is, in ChemChem, and I don't know how familiar you are with that, is there a way for us to easily define error bounds?
No, not in a ChemChem pseudo package.
Like, okay. So
That's what we have.
that
We are ChemChem based, but we use the 80s version of ChemChem.
Okay.
I have a little bit of problem with running something that doesn't have source code. Okay. If something is wrong, it's just by a wacky principle I always had that I like to run a code that has source code. Because if something goes wrong, I better know. I want to know. Okay. I don't want to blame on the code developer because it is my responsibility. Other issues? Yeah, go ahead.
First of all, thank you for the presentation. But there's one thing that I feel very uncomfortable about here, and that is that you seem to have imposed a structure on the kind of uncertainty that you have on the parameters. Is there some way you could justify that? Like, in all your plots, it appears as if you have imposed a uniform distribution or a Gaussian distribution.
That is the dirt under the rug of this method, so to speak. We are assigning either a uniform distribution or we assign a Gaussian distribution. Okay. What we have tested is the following. This is a two limiting case. Okay? You can have other distributions, they're all similar to Gaussian. Turns out that if you deal with one or two rate parameters, it matters in the system. The minute you deal 20 rate parameters, the central limit theorem kicks in. It kicks in and it tells you that it doesn't matter what distribution form you assume. It doesn't impact your final prediction. Yeah.
I think the central limit theorem kicks in when you have infinite data. With limited data,
That's right.
it's very likely that you have multiple limits.
Right, you're right. What I can say is the following. We tested this central limit theory on this kinetic problem, if I can find this plot. That's the representation of the central limiting theorem, central limit theorem applied to the current problem. Okay. Now the issue here is that the probability density function for a random variable, if you consider one, that's the uniform distribution, and if you start to increase the number of variables you consider, it quickly converges to a distribution you really don't have to worry about. And we're dealing about 20, 30 parameters. Okay. And we've done this problem fairly carefully. The conclusion is that at the end, if you do various direct Monte Carlo sampling without assuming distribution, you assume other distribution, it won't affect your result. It will affect at the end, after you project uncertainty back onto rate constant space, it will affect the shape of the feasibility space. That is a more severe problem. Okay. But you cannot, right now, you can only do with what you know. If a rate constant has been only measured once, what do? You have no choice. You cannot define the statistics, so you can have to rely on the best knowledge you have of this uniform distribution. Okay? And when you have enough data, you go to that. The point is, either this or that, or mixture of the two, after you consider enough variables, it won't matter for the time being. Okay. As far as the model prediction is concerned. All right, so we have about 10 minutes, and I wanted to talk to you a couple of problems, open problems. Okay, I want to pose one question. First, the current approach to turbulent combustion modeling, at least the next 20 years, is defined as you develop reaction mechanisms, models. You develop LES type of turbulence model. You verify the parameter in LES turbulence by DNS, direct numerical simulation. The idea is once you verify your LES model, you're going to be able to combine this reaction chemistry with certain method mechanism reduction to get a prediction. And this type of stuff that Professor Tianfeng Lu does in a DNS site. Okay? That's the dominant thinking behind almost everything we do at the fundamental side of combustion. I want to challenge this notion. Challenge this notion from the combustion chemistry side. Let me tell you why. Whatever we do, if you write down a reaction mechanism, you're writing down two things implicitly. The first you're writing down is the potential energy surface. Second, what you write down is the rates occurring on this potential energy surface, dictated by this potential energy surface. Okay? You have path width. Potential energy surface also dictates the path width. You will forget that the higher part of the potential energy it chooses from the reactants to the product, it chooses the most likely path. That's the lower lying energy path. Okay. From pathway, you have reactions. You collect them. Now we have a few thousand of them to about 100,000. You go back to you say, with the rate constant, I predict, just one example, heat release. Right? And from that, you get flame speeds, so on. The other things, you have radical growth that gives you ignition and whatnot. Heat release, that's enthalpy. You are predicting enthalpy release rate. Enthalpy is kinetic energy, as far as sensible enthalpy is concerned. Right? And potential energy added to sensible heat is what? Total energy. So if you can follow the dynamic process running down this potential energy surface, why do you have to worry about that? Total energy is conserved. If I can determine the evolution of potential energy, just like how I predict snow, wintertime, melt, running down the mountain and hills, eventually ending into the ocean, I can bypass this and go straight to that. Is that possible? That's problem number one I pose. If it is possible, we bypass detailed reactions. We bypass many unnecessary reactions that got dumped into a reaction model. One of you asked me this question, stated this very earlier. You're absolutely correct. Most of the reactions we dump into a model are not useful. They should not even be there, but they are there. Flip side of the problem, still, you cannot prove that all reactions that ought to be there are there. So that's an important problem that we need to consider. The notion of developing detailed reaction models, and you must start there before you can reduce it, get to the turbulence code, may or may not be the standard approach. I sure hope 20 years from now, one of you or all of you will think, oh, that was the past time, the new way of dealing with this problem. That's the first part I want to pose. We have no time to discuss it, so that's okay. The second problem I wish to pose is the following. Okay. We all take those governing equations responsible, for example, for flame propagation for granted. They're in a textbook. We talked about throughout the week the assumptions we made, starting from how we determine a specific heat. We didn't have the time to discuss the problem with transport coefficients. Okay. The first thing is I have to say is there's so many assumptions in that governing equation and the parameters that goes into the governing equation, and I encourage you one day to spend one weekend, write down all the assumptions. Okay? And start to fiddle with some of them. I'll give you one example. When you solve the flame code, you have the convective term. For species conservation, you have the convective term. Okay? You have the diffusion term that's responsible for how species move spatially due to concentration gradient. You then have the reaction source term, right? In a steady state condition, you add 3 terms together, they're equal to 0. All right? But think about this problem a little bit. All right? First of all, what is the origin of diffusion? Random motion of molecules. Okay? The random motion of molecules slowed down by molecular collision. Correct? So the molecular collision and temperature and the pressure determines diffusivity, diffusion coefficient. Then you look at the reaction source term. What is the origin of chemical reaction and the reaction rates? Also collision. Correct? But in that governing equation, if you dig deeper down, a little below that, you realize these 2 terms don't talk to each other at a fundamental level. As if the collision leading to reaction does themselves. Collision of diffusion does by themselves either. They don't talk to each other. I'll give you an example. In a flame, you have a hydrogen atom diffusing from the flame zone into the pre-flame region. It shall recombine with molecular oxygen O2, forming the HO2 complex after collision. This HO2 complex, remember, has a finite lifetime. So oxygen, being heavy, will carry the hydrogen around for a finite distance. Reaction may occur, leading to O plus OH, or in other cases, kick off the hydrogen back. That second process is decidedly non-Chapman-Enskog, because Chapman-Enskog theory of molecular diffusion assumes I always have elastic specular collision. The phenomenon of oxygen molecule carry the hydrogen atom around for a finite period of time is never considered in that conservation equation. That's the first example. Okay? Are we missing a term in the conservation equation? A coupling term. That's a foregone conclusion. There must be a coupling term missing. The question is, how important is that term? And under what circumstance you need to consider that term. Second example, we talked about this earlier. You get to tensor of atmosphere when the mean free path gets down to the length scale of the chain length of an alkene molecule, say a couple of nanometers. Even your convective term falls apart. Because how do you carry a large alkene molecule through a flow? The large alkene molecule, by argument of drag, has to orient itself. With a certain degree, it can waggle as a Brownian rotation. Okay? What is the temperature? You're modifying the fundamental statistical mechanics. You must modify the fundamental statistical mechanics to account for this mixture. You can argue, well, under that condition, the ideal gas law breaks apart. You can account for it there. But we're not doing it, right? Okay? Those are 2 little problems. And you can extrapolate from this point and find many, many problems. Purely because for historical reasons, those equations were written into textbooks and written into review papers. You don't challenge them anymore. And do challenge them. It can be a lot of fun. And you just never know. There's something new will come out of it. That's methodology development. Okay? So while you're doing research, you don't have to always do research for writing papers and having a purpose. Sometimes you wanted to just wander off. Do something for the fun of it. And then something happened, and you come back and say, we forgot this stuff, whole pile of paper on the side of your desk. You pick that up, and then one day you may be able to make a major impact by looking at those problems. Okay. We said that there's so many parameters we need to worry about. But at the end of the day, I always wonder that what if I have missed the physics? And that problem is a whole lot more difficult to uncover, especially for a mathematically underdefined problem. And I can't tell you for sure that those fling speed we predict, or I predict, the shock tube ignition delay I calculate are fundamentally correct because I'm not considered all the physics. Okay? So I'll leave the discussion here. It has been a long week. Thank you very much. And I be happy to answer any question you may have. I'll stay here this afternoon and into the party time. The party time. Can I call it party?
Yeah.
Okay. The farewell party.
You will stay here tonight. You guys call him up. It's going tomorrow.
All right. Lunchtime, right? Yeah. Thank you very much.